Greetings, gents, and hello, everyone out there for our monthly Rockin pop-up. My name is Marisa. I'm the Public Programs Manager at the Santa Cruz Museum of Natural History, joined as ever by Gavin and Graham, the Geology Gents. And today we're talking about the planets, right? The solar system.
That's right, Marisa.
Those are some pretty big rocks we're going to be talking about today. Can you guys name off all of the planets in order, just off the top of your head? By the way,
we could try. So there's Earth, Graham, obviously, and there's Saturn and Venus.
What about in order?
Ooh, that's pretty hard. That's 8 names in a row to keep track of. If only there were an easier way to keep track of them.
Right. So if I've learned anything from my intro geology classes, guys, I think that a good mnemonic device is the best way to remember things in order.
Please excuse my dear Aunt Sally, or
exactly
I don't remember what that stands for.
Right.
I think that's an order of operations in math.
Thank you.
There you go. Yeah. There you go. So let me hit you with one for the planets, and then maybe we can get them in order. So Here's a funny one. Many volcanoes emit mulberry jam sandwiches under normal pressure.
Who comes up with these things? Many volcanic eruptions?
Many volcanoes emit mulberry jam sandwiches under normal pressure.
Many volcanoes, Mercury, Venus, emit
Earth.
Mulberry.
Mars. Jam.
Jupiter.
Sandwiches.
Saturn.
Under.
Uranus.
Yep. Normal.
Neptune.
And pressure. And here we get contentious.
Ooh.
But is Pluto a planet, Graham? I'm setting you up. This is a loaded question.
Technically, by the working definition of a planet, which is all words, this is truly semantics. But Pluto is not a planet, and we won't talk about it today. But as a part of this trilogy of the Earth among its family in the solar system, we'll talk about it 2 months from now when we talk about the smaller bodies in the solar system, the non-planetary bodies.
Okay. So this is the start of a 3-part series, as you just mentioned. So we'll be doing this through April, looking at our solar system. But since we just decided that Pluto's not a planet, Gavin, do you have one that's a mnemonic device that excludes that final P?
Yeah, let me see if I could dig one up here.
I remember.
What about
the original? My dear Aunt. Wait, no, not my dear Aunt Sally. My very
educated mother just served us noodles.
Okay.
Oh my gosh. Mulberry jam, noodles. You guys are making me hungry.
It is lunchtime.
For sure. Yeah.
All right. Well, since we're all starving now, maybe we should get to it. So why don't you guys take it away? And then for all of you joining us live on Facebook, if you have a mnemonic device that you want to recommend for the order of the planets in our solar system, please leave them in the comments. We would love to read them. We'll get to them at the end. And if you have any questions or comments throughout the way, drop them there. All right, take it away.
All right. Well, I'm feeling hungry enough to sink our teeth into some terrestrial planets then.
That's right. Kind of rocky though. There's not the best to eat.
They'd be crunchy. You could chip a tooth.
Yeah.
All right. Well, let's dive in. So these are the 4 planets we're going to talk about today. My very esteemed mother is as far as we'll get today. And so let's dive in and just sort of, get an appreciation for what all we're talking about here. So through the course of our Rockin pop-ups, we've just about always been focused here on Earth. And so now we're looking at some new territory, right, Gavin?
That's right. I have to admit I'm biased towards Earth. It's by far my favorite planet. But as we go through, there's a lot to learn when we examine all of the other planets in our solar system. And so you can see you've laid this out nicely for us, Graham. And so this preserves the size, correct? So this is the relative size of each planet?
Yeah, that's right. So including the sun, we've got this great big ball of gas here. Some large but far smaller, mostly gassy bodies, and then these rocky, smaller planets in the interior. And so, like you said, this preserves the size, but not how close they are to each other. So here's another image to sort of look at how they sit relative to each other. And then this little inset here points out what their orbits look like, right? And so these things are moving in circles, just close to circles, not quite, but more or less a circle around the sun.
Okay, and so we're even though you might think about Mars as pretty far away, we're still snug. We're right around our big warm sun still, right, Graham?
That's right. That's right. Yeah, everything here is within about one distance between Earth and the sun, what we call an astronomical unit. So Mars only reaches out about 1.5 astronomical units. So when we're thinking of the not giant planets, our inner planets, they're pretty close to each other on human length scales, enormously far apart,
Right.
but pretty close on planetary scales. And so, like we said, we're going to be focusing on these terrestrial planets. So what do you mean by terrestrial, Gavin?
That's a good question, Graham. Well, terra, you're the Latin person. Terra means earth, right? So
That's
earth.
right.
So we're thinking about planets with solid rock when we say terrestrial planets. Planets made up mostly of solid rock.
That's right. Exactly. Rocks that are recognizably Earth-like. They've got, most of them is solid rock. They'll differ in the details, but it's that rocky body is what makes our planets terrestrial. And we were just having a conversation about this before we hopped on here, about why is it that all of our terrestrial planets are sitting on the inside rather than the outside? And we'll talk about this a lot more when we start thinking about meteorites. But essentially, these ones are rocky and not as gassy and icy because they formed closer to the sun where it was warmer. And so a lot of those ices had evaporated away. And so there was only really rocky stuff available, a little bit of water, right? We've got oceans here on Earth, but it was mostly just rocky stuff available to put these things together.
And Graham, I really like that fact because, it makes sense in my brain. You see all of these rocky planets really close to the sun in terms of their orbit today. And they formed pretty much there when they were forming in the proto solar system, or the beginnings of the solar system. So they formed too close to the sun, and it was too hot to keep all of the water around, all the gases around. So they couldn't keep them. The ones further away from the sun could keep them because it was less hot, right?
Yeah, that's a perfect way to put it. And this is one of those, I feel like, rare moments in Earth and planetary science where things are kind of just as simple as they seem. So yeah. It's nice that it all makes sense.
Yeah, makes sense.
Well, if we're going to talk about Earth-like planets, I say we start with the namesake of them. So Gavin,
yeah,
we've spent a lot of time talking about Earth, but give me an overview of Earth. If you were to describe Earth to someone who had never seen it before, what's special about this place?
Yeah, that's a nice tee up, Graham. I like that question you give me. So Earth is a terrestrial body, in that it's made mostly of rock. If you look at this top left image here, Earth is differentiated, which means that it's made up of a core. We have an inner and an outer core, where our inner core is solid and our outer core is liquid, and that core is metal. And so when I say differentiated, I mean when it first formed, it stratified by density. So your very heavy stuff, like your metals, sunk into the middle of the planet. So it has a core. Then outside of the core, it has a mantle, which is basically distinguished by what it's made out of. And then outside of the mantle, you have a crust, and that's our brittle part of our Earth. And as humans, we've only ever interacted with this part, the outer crust. Now, you're asking me to describe to some extraterrestrial alien, maybe, what the Earth is like and why it's special. Well, the Earth has this thing called tectonics. That brittle crust on the outside is made up of little tiny plates. I shouldn't say little tiny. They're they're sometimes large, but it's made up of plates that sort of move around. And as they move around, they crash into each other, they dive beneath each other, and they create our mountains and our valleys and our rifts. So plate tectonics is sort of geologists' like #1 unifying theory about understanding the Earth. Now, the third and final thing that I would say makes the Earth really special is the fact that it has water in many phases. So we have lots of water on our surface, and Earth is just the right size to have just the right amount of gravity to hold all of that water. So, and it's also just the right temperature that water exists as ice, which we've talked about on our poles where it's really cold, but throughout the rest of the planet, as Santa Cruzians know pretty well, you have oceans, liquid water, and we also have our very important atmosphere, which you can see as this blue veneer on the top image of gaseous water. So it's got water in 3 phases, and that drives the rest of it, because without the water, you wouldn't have the plate tectonics, and you'd look more like the moon, just some solid ball of rock.
Yeah, beautifully put, Gavin. And I think these are these really defining characteristics of the Earth, and they help us understand all the rich geologic processes that define our home. And so, great, we've got our good foundation for thinking about what is the terrestrial planet. And so now let's start skipping around the solar system.
Yeah, and we'll sort of use Earth as a metric, because it is a terrestrial planet. So we will, as we go along, Graham, I'm going to keep asking you, like, how is this similar to Earth? How is this different to Earth? I think that we can sort of gauge our way through the terrestrial planets that way.
That sounds fantastic. So let's head in as close as we can to the sun, to our first planet, Mercury. And so Mercury it's a little funky. We talked about how most of the orbits are circles. Well, Mercury's got kind of a squashed orbit. So all orbits are somewhere between a circle and a narrow ellipse. And most of the planets have really nice round, pretty uniform orbits. Mercury's it's a little bit squashed. It's a little bit more eccentric in the shape of its ellipse. And it takes about 115 Earth days to orbit the sun. But because of the way its orbit and the way that it rotates around are sort of synchronized with each other, it takes it a very long time to go through one Mercurian day. It takes 2 Mercurian years, in fact. So you can kind of see in this animation, if you follow this arrow, it'll take it 2 laps around to point back at the sun.
Huh. Okay, so Mercury has it all backwards in terms of the timings of the days and years. Our days are really quick. Our years are 365 times that day. Whereas Mercury, its years are really short. It only has 115 Earth day year, but its days are really long. For it to, rotate, since it rotates so slowly, its days are 2 years. 2 Earth years.
Yeah, that's exactly right. And so not only do you have this wild, confusing daylight on Mercury, but it means that when it's facing the sun, it faces the sun for a long time. And so during the daytime, it gets extremely hot, up to 800 degrees Fahrenheit. And at night, it gets extremely cold, up to minus 280 degrees Fahrenheit. Truly hotter than any oven I've ever heated up, and colder than the coldest freezer I've ever seen by hundreds of degrees.
Yeah, you can make a mean pizza on the surface of Mercury in a day, and then probably a really, really cold batch of ice cream at night.
Yeah, talk about brain freeze, Gavin.
But Graham, so you have this picture over here, and first of all, the way we take this picture is sort of interesting to me. So Graham, we fly basically little tiny spaceships past these planets. What do you call those again?
So it's sometimes they're sent right by, and they're called flybys that they take these pictures of. But sometimes they'll go and do a couple laps around the planet, just like how the moon orbits around the Earth or the planets orbit around the sun. We'll send these instruments to orbit around the planet, and we call those orbiters.
Got it. Okay. And so we sent either an orbiter or a flyby. I forget which one towards
Yeah,
Mercury.
I think this is probably Messenger, but I'm not sure. I don't know my NASA missions very well.
Got it. Okay. But we sent a spaceship and we took this picture. And honestly, this looks a lot like the moon to me without maybe the highlands and the mare. So what does that tell us about the surface?
Yeah, that's a great point. Yeah, so we've got all these impact craters on the surface. And so it tells us that we don't have the same sort of erosive processes going on. And so one of the key things here is that we don't have continents relative to oceans, or at least not in the same way we do on Earth. And so we don't really have plate tectonics here. We don't have a lot of erosion here. There's no atmosphere. It's so close to the sun that any atmosphere has just been baked clean off of it.
Got it. Too hot. We boiled off all the water.
That's right. No water, no air. Mercury would be, if you're thinking about having an extraterrestrial summer home, this is not the place for it. Miserable times on the surface of Mercury.
Got it. Okay.
Cool. And so that's what the outside's like. Gavin, what's going on inside of Mercury?
Yeah, well, in terms of the actual layers, it has similar differentiation. So it's broken into a mantle, which is metal, a core, which is metal, and a mantle, which is that outer veneer of rock, and the crust, which is that really, really brittle part. But the mantle or the core makes up most of Mercury. It's got, relative to its body size, which is small, it has a really huge core. I really like that top image you put there, Graham. It's a big core.
Yeah, it's got an enormous core compared to the overall size of its body. And this is comparing core sizes versus the overall planet size. The planets are not all the same size, but you can see just how much of Mercury is made up of that core. It is really a metal-rich body.
Huh. Okay.
But still, no plate tectonics, right? So we have an interior structure kind of like Earth, but that doesn't mean that it's acting just like Earth.
Mm-hmm.
So now I've got a feel for, what the weather's like, what the interior is like. And so now let's talk about some geography. What's going on the surface here?
Yeah, so you actually have some water ice. That's pretty surprising. There's water ice at the North Pole of Mercury, Graham.
Yeah, so there are just these few little places where water has been able to hang on, and it's of course frozen, and it has to be in the shadows of craters at the North Pole. So only in these very, very special locations has Mercury held on to a little bit of water. But it's only because there's no atmosphere to carry heat around, and certainly that water never melts. And so yeah, so far, all we've talked about on the surface of Mercury are craters and impacts. Is that the only thing? Is Mercury kind of like the moon has been for the last 3 billion years? Just, things crashing into it and messing up the surface?
Well, you do have this collapsed magma chamber down here, Graham. And that is interesting to me, because when I think of a magma chamber, I think of plate tectonics, right? A lot of times we see magma chambers like the Sierra Nevadas in a place where we had a tectonic collisional zone, but we wouldn't really expect tectonics on the surface of Mercury because it lost its water so early. So what's going on here?
Yeah, that's a really good point, Gavin. And so this will be a bit of a recurring theme. We'll talk about bodies that don't have plate tectonics in the way the Earth does. Mm-hmm. And yet they still are hot inside, and they still want to release heat. And one of the beautiful things about plate tectonics is that helps move heat through the Earth. It helps it release heat from the interior, and that's a good thing for Earth. And it helps to localize where heat is released in volcanoes. But on a place like Mercury, you don't have subduction zones. You're not often generating new volcanoes. So sometimes that heat will pool up enough, and you can form volcanoes from that. Or you can also have melting and volcanoes forming from really big impacts.
Got it. Okay, makes sense. Non-tectonic related, but you still have heat in the interior from the accretion of the planet.
That's right. And the body wants to let go of all that heat.
That's right. Interesting. Okay. I feel like we've kind of done it. That's a pretty, for something kind of far away, we know a pretty good amount about Mercury, huh?
Yeah, absolutely. We've spent some time thinking about it. So yeah, let's hop a little bit closer to Earth. And oh my gosh, we totally
Thought
forgot.
about it. Yeah. Mhm.
We've never put we've never landed anything on Mercury. So we've never gotten a good close-up look of what the rocks on Mercury look like. All we see is this, gray image here. But this is a meteorite that fell on Earth that some folks have suggested might have come from Mercury. The data is still inconclusive right now. No one's really confident. No one's saying this rock that was found in the Sahara Desert came from Mercury, but it might have. We aren't certain it hasn't, I guess we can say.
Yeah, maybe a Mercurian rock. That'd be
Maybe.
cool.
All right. Enough of Mercury. Let's head to Venus.
Venus, yeah. This is an interesting one. I mean, again, some pretty interesting images we have here, Graham. So the left side looks sort of cloudy. You have a body that looks cloudy, and you say it's ultraviolet, okay? And so it's a composite image of what?
Yeah, so this is one of those false color images where folks took pictures of Venus with ultraviolet light and visual light, so light that we can see and light that we can't see, and kind of layered them onto each other to help make some of the characteristics pop. And what you can see here is it's a really cloudy planet. It's very smoggy, it's very cloudy, it's shrouded in these Venusian mists. And we'll talk a little bit about what those are in a little bit, but what it means is it obscures, when we look at Venus, and we'll show a picture later on of what Venus looks like just in visible light, there's no characteristics to the surface. It's all clouded out. And so we need to use orbiters, like you talked about, little instruments that orbit, and use radar off of those to actually map the topography here. So this is a false color image simulated by computers of the surface topography of Venus.
Huh. Okay, so we have thick clouds, but also a surface that has neat and interesting rock topography.
That's right.
Okay.
So we can let's zoom in a little bit. So
I also, Graham, just want to say that Venusian Mists, great band name. I like
this. I love it. We'll have to learn some instruments so that we can start that band.
Yeah. Anyway, that's an aside. Go ahead. Venus.
Sorry, you'll need to indulge me. What kind of music would we play?
No. Venusian Mist, that sounds sort of like maybe like some chill music, maybe.
You wouldn't say rock music?
Oh, I see where you were setting me up. That's good.
Or maybe we would play more atmospheric music. Okay, get me out of here. We gotta. Okay, so Gavin, some folks have said, I haven't been known to say this very often, but I have heard folks describe Venus as Earth's sister. Why would we call it that? Why would we say that Venus is that much like Earth?
Yeah, in a lot of ways, Venus is alike Earth. Its orbit is a lot like Earth's, as you can see from this little movie you're playing. It's relatively close to Earth, and so as we said, in terms of the heat and how you're making the planet, it's like Earth. And size-wise, that's another really important variable in how planets behave. It's very close to Earth in size. So in those ways, it is like Earth, and the interior of it is kind of similar too, right, Graham?
Yeah, and so similar position in the solar system, similar size, similar interior structure. Gavin, we might be just talking about Earth until we take a look at its atmosphere. And Venus is really, like, we talked about Mercury being a terrible place to put a summer home. Well, I would move to Mercury in a heartbeat compared to Venus.
Yeah. Sorry, you go ahead, Graham.
Oh yeah. So we'll give you a little overview of what the surface of Venus is like. So it's got this very thick CO2 rich atmosphere. So the atmosphere is 97% CO2. So on Earth, we have several hundred parts per million of CO2. Almost all of the atmosphere on Venus is CO2. But don't worry, there's also sulfuric acid clouds that are in that CO2 rich atmosphere. we've talked about how CO2 is a greenhouse gas, right? And so that greenhouse gas traps heat inside. And so the temperature on Venus almost never dips below 860 degrees Fahrenheit. So it's even hotter than the surface of Mercury all the time. This is an image of what Venus looks like just in visual light. So that might be through a telescope or just with a visual light picture. It is just this smoggy, sphere. You can't really see anything inside of there. And then when you get down to the surface, get through all those sulfuric acid clouds, there's 92 Earth atmospheres of air pressure, just absolutely crushing. Just a terrible place.
You have that whole dense atmosphere, which has mass just weighing down on you. So it's not only hot, it's not only acidic and gross, but it's also really, really highly pressurized. That doesn't sound like
it sounds like a terrible time. But one of the neat things about Venus's absolutely terrible climate is that we can use it as a way to understand what an extreme greenhouse is like. So we're very concerned with greenhouse effects on Earth. Folks do not need to worry. We are never going to have 97% CO2 atmosphere. We will never get that hot. But it is an interesting way to compare what these runaway greenhouses look like. And so, Gavin, the warmth and the heat here, this has really important implications for one of the most important molecules on Earth. What's going to happen to water on Venus?
Yeah, it's going to be too hot again. You're going to lose it. It just boils off. I could probably boil water at on my stovetop. I'm not going to get up to 860 Fahrenheit on my stovetop. So yeah, water's not going to stick around Venus very often.
That's exactly right. So this warm atmosphere is anything but humid. And so, okay, that's the air over it. But what's going on the surface of Venus?
Yeah, I mean, we're geologists. We got to talk about the rocks. This is something I learned while making this pop-up, but there was a lander on Venus, which you told me, Graham. This lander landed for what? It operated for 2 hours. It was a Russian probe that landed and took some pictures. So these are actual pictures on the top of what the rocks look like, huh?
Yeah, that's right. And the reason it only lasted 2 hours is because that nasty atmosphere was crushing it and corroding it as it landed. But so we actually have a picture of the surface of Venus, which is pretty incredible.
And then there are some very sort of familiar features still on Venus. You have impact craters, which are relatively young. And remember, we always think about the age of the impact craters because that tells us how often the surface of the planet is sort of reworked. And so these young craters make me think that it has been reworked. Is that right, Graham?
Yeah, that's right. And so, yeah, we've got these impact craters that are pretty young. We've got these great big shield volcanoes like the volcanoes on Hawaii. And so we've got volcanism in a big way here. We've got young impact craters. But because all of these are really quite young, some folks have suggested that the surface of Venus does get resurfaced every few 100 million years. And some folks have even suggested that, well, there's not plate tectonics like we see on Earth with rifting and subduction, that there might actually be these sort of episodes where so much heat sort of pools up in the interior of Venus that it ends up weakening and thinning the crust enough that it all kind of turns over and a new crust is built every few 100 million years.
That is fascinating. That is really, really cool. Very interesting in terms of Venus and how it resurfaces its crust.
Yeah.
But what else? Did we do it for Venus, or are we going to talk about anything else?
I think we did. I'm feeling good on Venus. So we covered Earth. And so let's check out the last, but certainly not the least of our terrestrial planets.
Yeah. Mars is gotten a lot of press these days on Earth. A lot of people are really interested in Mars because of its habitability. It's close enough to Earth. We've even landed a bunch of rovers on Mars. Like, Mars is really a like hotbed for scientific thinking recently. And so as we said, so we jumped over Earth's orbit. So Mars is actually outside of Earth's orbit. It's got a larger orbit. but it's relatively close, right, Graham, to Earth still?
That's right. Yeah, just it's maybe half as far from Earth as the Earth is from the sun. So it's not terribly far away.
Yeah, but it's smaller. It's a wee planet. It's about half the size of Earth, which again affects how much gravity it has, and that in turn affects the water on Mars, and we'll get to that. But the interior of Mars, Graham, again, it's differentiated. All these terrestrial planets are differentiated, but relative to Earth, what's it looking like?
Yeah, relative to Earth, it's quite similar. We've got an inner core, we've got a metal core, a rocky mantle on top of it. There's probably the core has probably cooled enough that it's not still liquid. Mars is just as smaller and as far away from the sun, so it's lost a lot of its heat. Unlike Earth's crust that has this basaltic ocean crust and this granite-like continental crust, Mars has just a mostly basaltic crust over it. But really, in a lot of ways, quite similar to Earth in terms of its metal, its differentiation, its metal, its rock. And so, a pretty familiar looking body.
Yeah. And so, Graham, I had mentioned something about the habitability. If you've seen The Martian with Matt Damon, great movie, but we're talking about humans trying to think if we could land on Mars and like have a civilization. And when it comes to habitability and life in general, the biggest question is water. And so NASA and all of the planetary scientists have been really thinking, like, is there water on Mars? Was there water on Mars? Is there currently liquid water on Mars? These are all questions we want to know. And so there have been a bunch of scientific discoveries, like the map in the top left, which see these geomorphic features on the surface of Mars. That is the like topography and the geometry of the surface, and think, oh wow, this might be evidence of modern liquid water, running liquid water. But it turns out that in our current understanding, we have not seen any evidence of liquid water on the surface of Mars. And the reason that happens is because Mars is really small, as we said, so it only has 0.37 times the gravity of Earth, which means that it's got very little surface pressure. It loses its atmosphere. It also is really cold. So the surface temperatures are at most minus 81. And so any water that'll be there will be transient anyway. In the modern Mars, it would just turn to ice right off the bat. But similar to Earth and Mercury as well, Mars has ice caps on its poles, right?
Mm-hmm.
And so this is liquid water, right, Graham?
Yeah, right. So there's no more liquid water on the surface. There's all sorts of these, stream beds, riverbeds that show that there was probably liquid water on it at some point in time, but we cannot see any evidence for it these days, or nothing that's really conclusive. But there's no running water on the surface. There is water stored away in these ice caps. That's right. So there's water, but not a ton that we can necessarily use just yet if we're trying to stay hydrated on Mars.
That's right. But as I said, because we've been studying Mars so much, we know a lot about the rocks, Graham, right?
Yep.
So if we've had these rovers, we've so far had 5 rovers on the surface of Mars, and some of them for really long time spans. And so the last rover that actually just died was on Mars for almost a decade, if I understand correctly. And it's driving around the surface of Mars and just making these measurements and looking at the rocks and taking pictures like the one up here. So this is an actual picture in the top left of the surface of Mars. And so we really know a lot about the geomorphic features, like how the surface of Mars has evolved and what it looks like. And so bottom right, this is a picture of one of the rovers on Mars. It's kind of cute. It's kind of like a looking rover.
Cruising around looking at rocks. That's my kind of machine.
That's right, a rover after our own hearts. And so, but we currently have not ever had a rover collect samples and bring them back to Earth. But that is in the plans for the next ones. So apparently the next rover, or maybe the one after that, is going to try and collect samples and bring them back. But like Mercury, Mercury is contentious, but we do have Martian meteorites. We have rocks that are from Mars confirmed. And I think, Graham, correct me if I'm wrong, we have several rocks from Mars, like many Martian meteorites.
Yeah, so there's like 270 or so confirmed Martian meteorites, and those have been super helpful for, we don't know where they necessarily came from on Mars. We have some ideas, but they do help us at least understand some of the Martian history.
Cool. So we know a lot about the geology. We also have these interesting images, Graham, and I'm looking for the dichotomy of the rocks on of the hemispheres on Mars. And so let's talk about that a little bit.
Yeah.
This thing called hemispheric dichotomy. Take me through it.
Yeah. So on Mars, when we often think of like the surface elevations on Earth, we've got our continents, we've got our oceans. The continents are the high point. The rocks at making the base of the oceans is our low points. And so that's how we sort of think about our different elevations. Well, on Mars, it's more that it's got really high elevations in the southern hemisphere and lower elevations in the northern hemisphere. So you've got this really low, flat northern hemisphere and this kind of raised, mountainous southern hemisphere. And yeah, it's really kind of wild looking.
Yeah, and like it's interesting because if you hit a nail on the head there, Graham. The southern hemisphere is like rugged. It's got a ton of craters. It's very, very cratered. And scientists think that dates back to ancient, very, very ancient terrains where you had lots of meteorites during an episode of meteorite bombardment called the Late Heavy Bombardment. So anyway, that was in ancient times, very early in the solar system, when you bombarded the surface of Mars with a bunch of meteorites and made all these craters. However, the northern hemisphere doesn't show that. And so folks think that the northern hemisphere is actually younger crust and it's been resurfaced, right, Graham?
Yeah. And so that could be anything from something geologic-like in behavior to a massive impact that really, reworked this whole area. Is that right?
Yeah. I think that it's still, if I understand correctly, I think that it is still a sort of a object of scientific study where we don't know why this is the case, but there are several theories. Like you said, it could have been an impact, could have been early tectonics. We're not really sure. So scientists are still trying to figure that all out, and they probably will soon.
Yeah, nice. And so we've got all these parts of the Martian puzzle. So when we put it all together, what's a trip around Mars going to show us?
Yeah, and I just want to say that Mars is special in that we really know a lot about it. We've studied it really hard. We've sent a lot of landers and probes there, so we can say a lot about Mars that we may not be able to say about some of the other terrestrial planets. And that is Mars has some very distinctive features like Olympus Mons. And that is a giant volcano. It's actually the tallest mountain in the whole solar system. I really like both of these pictures on the left because you could see that from space. That was a lot of lava that came out, and it's so big it just dwarfs any topography that's on Earth. You could see it. It just makes Mount Everest and Mount Mauna Kea just look totally small.
Wow, that is incredible. That's a big mountain, Gavin.
That is a big mountain, and so it's sort of an interesting feature. But here on the right, we have actually very important features about how we understand what the surface of Mars was once like. So the first thing on top is these dried riverbeds. And Graham, dead ringer, what are dried riverbeds? Like, why do they form?
There had to be a liquid flowing across the surface. And so at some point, and it's almost, we're highly certain this is liquid water. There's some cases where I think maybe liquid carbon dioxide might have played a role a little bit more recently on Mars, but something at this scale is very likely, this is a dead ringer for water, and there were rivers of water on Mars at one point.
Yeah, so we know we had river valleys and channels just like we do on Earth. So pretty neat there. So there must have been water at some time. We also know that you at least had tectonics. I've read some places that there have been recent finds of active tectonics. I'm not sure if that was if that held up to science over the years, but you definitely have had tectonics on the surface of Mars. And you have these big tectonic rift valleys like the one I show on the bottom here. This is a valley that would absolutely dwarf the Grand Canyon. This valley would stretch across the United States and is a really, really huge tectonic rift zone. So you had processes on Mars that were a lot like Earth.
That's incredible.
Yeah.
Oh
Yeah.
my gosh. Oh, so we've made our way through the terrestrial planets of the solar system, but we can also talk a little bit about terrestrial planets outside of the solar system. So this is an exciting frontier in astronomy and planetary science. It's thinking about rocky, terrestrial, perhaps even Earth-like and potentially habitable planets around other stars. And this is one of the more famous systems, the TRAPPIST-1 system, where there's not one, not two, not four, but 7 planets kind of close in, probably rocky planets, close in to this red dwarf star. It's a very old system. We obviously have never seen the planets this clearly. These are all artist depictions, but something astronomers are super interested in is trying to understand what are terrestrial planets like around other stars.
Super neat, Graham. And this is something you learn a lot more about this than I do. I focus my research on Earth more, but man, this is cool. It really does seem like a new frontier to learn about all of the possibly habitable planets. This is the type of science you dream about as a kid, huh?
Totally. Yeah. And so, yeah, we've got our planets here. Those are strange and mysterious in their own ways. And then there's a whole other level of peculiar planets around different stars. And I think that kind of brings us back to our terrestrial planets. And so I think we've covered it, Gavin. What about you?
Pretty much sums it up. Yeah, pretty neat journey we made there across the 4 in our solar system though.
Yeah.
So what's next?
So we wrapped up the inner part of the solar system. So Gavin, next month we're going to take care of the outer part.
The giants. Yes, you go further from the terrestrial planets, further away from the sun, and all the planets are just huge. They're giant planets. They're made of gas and ice, and I'm looking forward to diving into it next month. Huh, Graham?
Me as well.
Cool. Thanks, guys. That was wonderful. And I don't know if I'd ever thought of the solar system in terms of the inner planets being the ones that are close enough to have ice melt. Basically, I loved that. That was like a really great framework for me to think about it moving forward. I also started jotting down potential band names after Venusian Mist. I don't think anything came up that was quite as poetic after that one. So I think that's still the top contender, but other options, Earth's Sister.
Ooh.
Oh, yeah.
Metallic Core.
Mm-hmm.
Sulfuric Acid. That's probably already a band name. Sojourner.
Ah, yes.
And then maybe like Olympus Mons. Maybe
Olympus
like some sort of metal band.
that might also have been taken.
But yeah.
that
Cool. Well, I can't wait to jot down more potential band names next month. And I also wanted to I'm going to drop like in the comments here a link to other future museum events. We've got a lot going on, so we're happy to have everyone join us here live on Facebook every month for the Rockin pop-up. We also have other online events and a bunch of stuff happening out in nature and at the museum. So we hope that everyone out there will continue to engage with us as we await next month's Rockin pop-up. And with that, I think we'll say goodbye for now and see you next month.
sounds great. Thanks, Marissa.